Up to this point, we've looked at permutations, and now we want to talk about combinations, which sounds similar, but there's a major distinction between permutations and combinations, as you're going to see. So let's begin with this example. We have 5 sprinters competing in a race, and we'll call our sprinters A, B, C, D, E. And what we want to do is we want to award medals to the first, second, and third place finishers. First, second, and third. Alright, so what we could have, let me just write out a couple of possibilities here. We could have A, B, and C, A first, B second, C third. Or we could have B first, A second, C third. Or we could have A first, C second, B third, etc. And what I'm doing is I'm writing out all the orders just of these 3 people. Alright? And then, of course, we could have B, C, D come in, and C, B, D in that order, etc., etc. Okay? The point is that the order in which people come in matters. So these are all the same 3 people, but these 3 people are all coming in different orders, first, second, and third. So in this situation, the order matters, and that, of course, is what we call a permutation, as we've talked about. This is an example of a permutation of 5 objects taken 3 at a time. So there's 5 people, and we're going to pick 3 people to come in first, second, and third. And by formula, we can get that to be 5 factorial over 5 minus 3, 2 factorial. If you work that out, there's 60 different permutations. So now I've taken my question from above and I've changed it slightly. We still have our 5 sprinters, but now we're saying that the fastest 3 sprinters are going to qualify for the relay team. And we want to know how many different relay teams can be formed. The difference with this question, as you might see, is that the order of the first, second, and third place finishers doesn't matter. So all of these permutations, they are considered to be all one combination. The order that they come in doesn't matter. So whether it's A, B, and C first, second, and third, doesn't matter if it's B, C, and A first, second, and third, these 3 people are going to qualify for the relay team. And that's going to be one combination of people for the relay team. And similarly for the one that I was beginning to develop here, right? If I take all the orders of B, C, and D, and there would be 6 of them, this will all be considered to be one combination. And so you can see that the number of combinations in which order doesn't matter will be less than the number of permutations. In this situation, the order does not matter. And this is an example of 5 objects taken 3 at a time. That's a combination. So the question is, how can we get the number of combinations? If we take 5 objects and we want to choose 3 of them, choose means that the order doesn't matter, we can see that the number of permutations, we know that the number of permutations is 5p3, and we can see from what I was doing here is that if there's 3 items being picked, we don't care about the fact of all the orders of those 3 items. In other words, there's going to be, if this is one combination, but there's 6 permutations, there's 6 times the number of permutations as combinations. So what we need to do, we need to divide away the 6, which is the 3 factorial. And if I simplify this, remember that this was 5 factorial over 2 factorial. And then we're bringing the 3 factorial into it, which will be there. This is the formula for 5 choose 3. It's going to be our 60 divided by 6. So there will be 10 combinations, 10 different relay teams that are possible. And so just to generalize, an unordered arrangement of objects is called a combination, whereas an ordered arrangement of objects was a permutation. And we can get the number of combinations of n objects chosen r at a time by taking the number of permutations of n objects picked r at a time and dividing by r factorial, which will take away the repeats of the orders of those r items. And that can be reduced to n factorial over r factorial times n minus r factorial. And just as with NPR, you will find NCR on your calculator. So some examples with combinations. We want to know how many different committees of 3 people we can form from choices of 7 people. Now the main thing here is that you've got to consider whether the order matters in this situation or it doesn't matter. And because we just want 3 people, we don't care about who's picked first, second, and third. This is a combination. So this is 7 choose 3. And so that's 7 factorial over 3 factorial. This is our r, remember, over 7 minus 3 times 4 factorial. And you can work that out, and that works out to 35. However, if the question had been picking 3 people from 7, and the first person is going to occupy the chair of chairperson, the second person is going to be the treasurer, and the third person is going to be the secretary, then picking person ABC is different than picking person BAC. In other words, the order in this situation does matter. So that would be 7 pick 3, and you can work that out, 210 different committees. Here's another similar situation, but we have some constraints thrown in. Our 7 people consist of 3 males and 4 females, and we want to know how many different committees of 3 people. So we're still picking a committee of 3 people, but this time the committee must have 1 male and 2 females. How many different committees are there? And so, as we've discussed in the past with permutations, we need to consider the different groupings separately. We have our 3 males, and what we're going to do is we're going to choose one of them. Okay? And we have our 4 females, and we're going to choose 2 of them. Now I'm using choose because the order that I pick the females doesn't matter. If I pick Lynn and Betty, and then Betty and Lynn, that's the same combination. So it's a combination question. And then I combine these 2 separate categories with the fundamental counting principle. The number of ways to pick the males, for each of those ways, there's this many ways to pick the females. And you can then work that out with your calculator. Remember, to access this feature on the calculator, you need to go to the Math button, over to Probability, and then number 3. And one more example with all of this. We, again, have a group of 7 people. This time we have 3 males and 4 females, and we want to know how many different committees of 3 people that have at least 1 male on them. Alright, so at least 1 male means we could have 1 male and 2 females, or we could have 2 males and 1 female, or we could have 3 males and 0 females. And this is similar to a case situation that we talked about previously. We're going to work each of the individual components out separately and then add them together. Alright, and then within that we need to consider each of the categories separately. So we have 3 males, we're going to choose 1, and for each way to do that there are 4 females, we're going to choose 2. That's exactly what we did above. Our other situation is we have 2 males and 1 female, so we have 3 males to choose from, we're going to choose 2, and 4 females to choose from, we're going to choose 1. And lastly, we have 3 males that we need to choose from 3 males, so 3 choose 3. That's just 1, because there's only one way to choose 3 males from 3 males. And the same way with females, there's 4 females, we're going to choose 0. There's one way to do that. So this number here is just 1. And then you can work these other numbers out to come up with your total number of ways, which I've worked out to be 31. Now there's one other thing that I want to add to this video, and that's just talking a little bit about Pascal's triangle, which is a triangle consisting of a pattern of numbers that goes like this. Now I'm going to continue the pattern, but essentially what happens here is that these 2 numbers added give the number below it. Alright? So in the next line, I know from the pattern that I'm going to start with a 1. These two numbers add to 4, so 4 goes below it. These two numbers add to 6, so 6 goes below it, etc. 1 and 4 is 5, 4 and 6 is 10, 6 and 4 is 10, 4 and 1 is 5, and then 1. And you can continue this pattern on and on. And there are lots of patterns within this triangle that actually apply to a whole pile of things. But the reason I'm bringing it up now is that these numbers are actually the numbers for combinations. 0 choose 0 is 1. This is 1 choose 0. This is 1 choose 1. In this row, this is 2 choose 0. This is 2 choose 1. And this is 2 choose 2. And so this row is the 3 chooses, the 4 chooses, the 5 chooses, the 6 chooses. Specifically, 6 choose 0, 6 choose 1, 6 choose 2, etc. And so you can get numbers for specific choose values from the triangle if you wish. But again, this triangle is loaded with lots of other patterns and uses that I'll let you explore on your own and through your discussions in class. And Pascal's triangle will be useful when we study the binomial theorem in the next video. And here's one other way that Pascal's triangle is useful as well. You remember in a previous video we talked about determining the number of ways to get from point A to B, and we did that through the use of permutations. Well, I'm going to take another approach at this problem, and what I'm going to do is I'm going to start at A, and I'm going to ask myself, how many ways are there to get to this point? Well, there's 1. How many ways to get to this point? 1. How many ways to get to this point? Well, I can see that there's 2, because I can go this way and this way. All of these points going down, there's 1 way to get to them. 1 way to get to the points going across. How many ways to get here? Well, if I count them, there's 1, 2, 3. And similarly, there's 3 ways to get here. And you can maybe see what's happening, but the numbers of Pascal's triangle are showing up as the number of pathways in this pattern. So if I keep Pascal's triangle going, specifically 1 plus 3 gives me 4 here, 3 and 3 gives me 6 here, 3 and 1 gives me 4 here, 4 and 1 gives me 5 here, 6 and 4 gives me 10. And if I keep following the pattern, I can find that there are in fact 70 ways to get from point A to point B, and I can do it, instead of using permutations, using Pascal's triangle.